Okay, so kind of starting to talk through this stuff here. If you remember this, the same exact section almost is in your Algebra 2 stuff from Chapter 2, I think. We just did it in Algebra 2 like last week. So hopefully this should kind of be a review. So inverse variation just in general, as one of your variables increases, the other decreases. That's always going to be set up as some sort of k, or your constant of variation, over your independent variable. Sometimes this independent variable is just by itself. Sometimes it's like squared or something like that. So if it was squared here, that would just switch to a negative power of 2 there. So a couple things there. Your k can never equal 0, because if we did 0 divided by anything, that would just always give us a 0. So that's not going to be helpful. And then it's always going to give us, you can either call these hyperbolas or hyperbolas, just kind of depends on how you want to pronounce it. There's some pictures of what these look like in your packet. So if you go kind of past the examples in your packet, these are pictures of hyperbolas. So hyperbola. Depending on what your k value is, they're going to look a little different. So if your k value is positive, so that's kind of what they're showing right here. If your k value is positive, you're going to be in the first quadrant and the third quadrant. If your k value is negative, you're going to end up being in the second quadrant and the fourth quadrant. So setup is very similar, but just if it's a positive number, it's going to be there. If it's a negative number, it'll be in those ones. And then again, it can't ever equal 0, because then you just get 0, and that's not helpful for us. Okay. So just some things that happen with each of those. You're always going to have horizontal and vertical asymptotes. So asymptotes, like we've talked about before, are basically places that it's going to get really, really close to, but it's never going to cross. So you'll have that at your x-axis and your y-axis on both of those. And then your domain is all real numbers except 0. Reason for that is if we've got that equation, y is equal to k over x, can our x value ever be 0? No, why not? Can't ever divide by 0, right? So that's why it's never going to be that. And then if it can't be a 0 there, then we're never going to be able to kick out a 0 either, because your k can't be 0. So yeah, so those will always be our asymptotes. Okay, so then on our example sheet here, we'll go to example 1 then. The thing that sucks about these is I don't know if there's a way to do this on the calculator like we've been doing, like linear regression, quadratic regression, that kind of thing. I don't think that there's a button on the calculator we can push for this, so I think we have to do these out by hand, which kind of sucks, but we'll get through it. So it says the average song size in, I assume that's like megabytes, and approximate number of songs for a sample of 32 gigabytes, I assume, MP3 player. Do you guys even know what MP3 players are? Okay. Makes me feel old if you don't know what they are listed in the table below. And then they've got your average song sizes there, and then approximate number of songs on that MP3 player. Okay, so what they want us to do is they want us to come up with a formula for this. The sucky thing is they don't really tell us anywhere that this is the inverse variation stuff. If it's something on the test, I'll tell you it's the inverse variation. I'll tell you that like you're using that type of formula. I wish they had that here, but for some reason they don't. But basically we're going to set up an inverse variation for this. So find a formula that gives average number of songs that will fit on the MP3 player as a function of average song size. So how I would set this up here, again, if it was on the test, I would tell you it's inverse variation, but I would go number of songs is equal to, and then our k is our constant of variation, and then we're going to divide that by our independent variable here would be the s, the number of songs, or the average song size, sorry, size of songs. Okay, so then what they're going to want to do, that's like our general equation. From there, they're going to want you to figure out what the k value actually is. To do that, I would just pick one of the ordered pairs here in our table and then plug that in and find the k. So here, the one that I used on the example, I'm just going to use that. It was the 4.9 and then the 6500. You could use any of those. Your k values will just vary a little bit. This first column here is our s. Second column is our n. So what I would do is I would just treat this just like an ordered pair and plug that into my spots here. So the 4.9 is going to go in for the s. I'm trying to find my constant of variation, the k. And then the n that goes with my 4.9 is that 6500. So I'm going to put that there. And then you would just want to solve for your k. So to get ready to divide there, you would multiply by 4.9 on each side. and then your k would end up being 31,850. When you multiply that out. So that would be our constant of variation. So then what we'd want to do is we'd want to take that k value, put it back into that general equation we came up with. So n would equal, we're going to swap that k value in we just found, over, and then our s just goes in there. So that would be the setup of our equation. So 31,850 divided by our s is equal to the n. And again, hopefully this is kind of clicking with some stuff we've done last year, hopefully. Okay, and then it says graph the data and the model on a single set of axes. I'm just going to graph it on the calculator and then just do a rough sketch of it instead of trying to do it all out by hand. I think that's going to be the easiest way. So I would just go to our table like we usually do, so stat, edit, clear out what you got, and then I'm just going to type this into our table there, so like the 3.6 in the first column and then so on there, so I'm going to type all those in. And then once we get it typed in, then we're going to just do like a general scatter plot of it. So we'd have to go to stat plot, so second, and then the y equals button for stat plot. We're going to want to turn that first one on. Probably still set up as a scatter plot like we've had it before, and then you got list 1 and list 2 is what we're using. And then we're also going to want to zoom that in on our statistics, so you want to go zoom and then stat. And then if you hit enter, it should take you to the graph of that. It kind of just gives you the general graph. The other thing we can do with this is we just figured out what our equation was there, right? That 31,850 over s. Couldn't we also type that into our y equals and graph that along with our scatter plot? Yeah, so I go to y equals, clear out whatever's in there, and I go 31,850 divided by our x. And then graph that. And it should hopefully kind of look like it's kind of going through some of those points, right? Because obviously that was our goal, is to fit it to those points. So like I said, I'm just going to do a sketch of this. I'm not going to do like a whole out graph on this because it's going to take forever. So I just sketch out something like that. Across the bottom here is our song size. Up the side is a number of songs. And then I'm just going to kind of eyeball where I think the points probably are. And then I'm also going to draw in that curve. Looks like my marker's not in. Okay, and then once you get that kind of sketched out, you can see that that kind of fits okay, but obviously there's, one kind of there that's not fitting and kind of some in there that aren't fitting. So then they're going to want to actually make us use residuals, so like the observed minus the predicted, to figure out like how much we are actually off by. So what I'm going to do is I'm just going to make my chart over here just a little bit bigger. That way I can just kind of keep everything lined up. And I'm going to make another column here that's my predicted values. Oops. Predicted and then another one that's actually my residual. And our predicted ones is gonna be when we plug in to our equation that we just figured out there, that 31,000 divided by 850, or 31,850 divided by S. And then our residual is always our observed minus our predicted. So we'll take whatever's in this list minus whatever we get for the predicted. That'll give us our residuals. Okay, so I would just take each of these and plug them in. So like here, I'm going to plug into that formula, 31,850. My S value is 3.6. So I just go, oops, quit. 31,850 divided by 3.6. Get that number there. 8,847. I'm just going to go like 0.2. I'm just going to go to the tenths. And then I just keep doing that for all my letters there, or all my numbers there. So I go 31,850 divided by the next one, and just keep doing that out. Do you guys care if I just give you the numbers instead of plugging it in? Okay, I'll just give you the numbers. I'll zoom it in so you can see them better. So that second one there was 6,776.6. Next one, if I can read my handwriting, is 7,077.8, 7,583.3, 7,768.3, 5,491.4, 6,500 right on the dot. And the reason for that is that's the point we used to plug in to come up with that equation, so that makes sense that it worked out perfectly. And then the last one is 6,245.1. Okay, and then to find our residuals, it's always our observed number, so our original number here, minus our predicted numbers, so the ones that we just came up with. So you're just taking like the 8,000 minus 8,847.2, which would be negative 847.2. And then you just keep doing that for all those. So always the observed minus the predicted. So the next one is 223.4, 122.2, 16.7, 31.7, 8.6, 0, because again that was the one that we used to make our equation. And then the last one's 54.9. And those are our residuals. Okay, so then they want us to know, after we did all those residuals, it says use our residuals to assess the quality of your model. So if those are our residuals, what do you think? And again, residuals, like how far our predicted one is away from the original one, or what it actually was. So what do you think, good or bad? I think it's good for parts of them. Is it good for the whole thing though? No, so it's not horrible, but there's probably something better that might fit, right? Because if we look here, like this one's off by like negative 847, and if we kind of look at our graph, that makes sense that it's way off there. And these don't look super far off because they're like the way our graph is kind of zoomed, it doesn't seem like a lot, but still being off by like 200 and something, that's still probably pretty far off, right? So there's probably a better method that would work for this. So I would just say something like, we could just say probably a better method. We can just leave it at that, probably a better method. And that's the thing when you do it by hand and come up with your equation there, like we could have used any points, so maybe if we used another point on the graph, it would have been like a little bit more accurate or less accurate, but obviously if we do that for all of them, it's going to take forever. But yeah, that's our best guess on that. Okay, and then it says if we are actually using our thing that we came up with here, we're supposed to figure out about 10,000 songs would correspond to what average song size. So then we're just going to take that 10,000 and plug it into that formula that we came up with there. And the 10,000 would be in our song size part, so that would be like 10,000 is equal to that constant of variation, 31,850, divided by our S. And then in a case like this, when our S is on the bottom like that, do we like it when the variable's on the bottom? No, we do not. That makes it a pain in the ass to solve. So what I would do is I would get that variable off of the bottom, so it's division here. So to get it to the top, I'm going to multiply by S on each side, because then now it's off of the bottom there, and I've got 31,850 is equal to this, the 10,000 times the S. And then now that it's on the top, now I can solve it just like a normal problem. So to get rid of the multiply there, we divide by that 10,000 on each side, and then our S would be equal to 3.185, and then we were measuring all that stuff in megabytes. But again, if you picked different numbers for your original problem there, like if you picked a different ordered pair to start, your numbers will be off a little bit on all this stuff, so it kind of just depends on what you picked out. And like I said, there's probably other ones that we could have picked that might have been a little bit more in lines, but there's also probably worse ones. Like if we would have picked this point here, we probably would have got a worse looking graph, and it wouldn't hit as many of them, so that's why we kind of picked one in the middle there. Probably that one, I would guess, since it's going through that one. But yeah. Okay, cool on that? Alright, back to our sheets here. And next we got inverse squares. Okay, so this inverse square stuff, it's basically the same exact formula. It would probably help if I had that there. Sorry, I messed that up. Did you guys get that it said inverse square on top of that? That's my fault. I thought that I had all of it on there. How about that? Inverse square. Hopefully you got room to squeeze that in. So inverse square is the same exact thing as what we were just doing with the just inverse variation in general, except for now it's a squared on the bottom. So that makes our picture look a little bit different. These are the ones that look like volcanoes. So again, they're back on our sheet here. It says example 2, but you can just cross that out. I would write next to these that this is the inverse square. And then they give those formulas there as well. So, like the k over the x squared, k over the x squared. And then, again, depending on if our k value or our constant is positive or negative, if it's positive, our volcano is going to be on the top. If it's negative, our volcano is going to be on the bottom. And again, it's never going to cross those zeros again. So these would be our vertical and horizontal asymptotes again at 0 for both of those. And then same thing over there, horizontal and vertical asymptotes. The domain and range is slightly different here. So domain for both of them is still all real numbers except 0 because again, it can't be the 0 there, and it can go however far right and left. The range, though, depending if it's a positive number or a negative number, here our range would just be the ones that are bigger than 0 because it's on the top. Here our range would be the ones that are smaller than 0 because it's on the bottom. Okay? All right. Okay, so what do we got next here? Make sure I don't actually skip anything again. I think we're to the example sheet. Okay, so back to this here. Should be this one, intensity of light. Okay, so intensity of light from a point source is inversely proportional. See how it says like inversely proportional? That's what I'll do on the test. I'll tell you that you're using this kind of setup. I won't just leave you in the dark on that. So inversely proportional to the square this time of our distance. Suppose that at a distance of 5 centimeters, light intensity is rated at 600 lux, I assume. What will the intensity be at a distance of 10 centimeters and then at 23 centimeters? Okay, so same as before, I would set myself up a little equation here. We know it's inversely proportional, so I'm going to have something like that where my k is on the top. And then it says my intensity is inversely proportional. Intensity, I'm just going to go I for that. And then my inversely proportional is there as the square of the distance. So I'm going to go distance squared. And then it gives us two pieces of information. So it gives us that our distance of 5 centimeters goes with an intensity of the 600 lux. So I would take those two things that I know and use them as my I and my D into my equation here to find my K. So I would take that intensity of 600 is equal to my K over my distance is 5. And don't forget that that's squared. And then now that we got to set it up, now we just solve that out for K. So 5 squared would be 25. So K over 25 is equal to 600. And then to get rid of the divide by 25, multiply by 25 on each side. So our constant of variation I've got is 15,000 on my sheet. And then kind of similar to the one we did before, when we plugged in our point, we would just take that K value, put it back up in there to our original. So like I would be equal to that 15,000 divided by D squared. And that would be the setup of like our general equation there. And then they actually want us to figure out some specific ones. So what's our intensity at a distance of 10? So then I would just take 10, put that in for my distance. So my intensity of the light is equal to that 15,000 over 10 squared. And then I just solve that out. 15,000, 10 squared would be 100, right? So 15,000 divided by 100 would be 150. And then that intensity was measured in that lux, whatever that is. So that'd be for a distance of 10. And then I'd just do the same thing out for, they switch it to a distance of 23 centimeters. So I just do the same thing, intensity is equal to that 15,000 divided by, this time 23 squared. And then I just do 15,000 divided by the 23 squared on your calculator. And then you would get, I got a decimal number here. So let's go approximately 28.355 lux. And if you think about that logically, like if you're thinking about flashlights, doesn't actually I have a flashlight here. If I'm really close to it, isn't that pretty high intensity of light? If I'm really close to the wall, and then as I get further away, is it really intense light anymore? No. So as my distance increases, my intensity, as my distance gets bigger, my intensity goes down. So that's kind of what they're getting at there with that lux stuff. Okay. All right. I think there's one more little bullet thing right here. Yeah, a couple more bullets, and that would be it. So those last bullets just point out that if you have any like power function there, so like x to the power of whatever, doesn't matter what that a value is out front, you can do the reciprocal of that by basically flipping it over. So then it would just be 1 over whatever that is. That kind of goes along with this inverse stuff. That's why it's called inverse variation, because they're inverses of each other. So, okay, so that's it. So assignment there, page 129, 1 through 9.